today. Thank you all for showing up.
Yeah.
Yeah, that's right. At least I know who my good students are. Alrighty. So last time we had found that the specific heat at constant volume was equal to 3 halves n tilde the number of moles per kilogram RT, R being the gas constant. And what we should note here is that du, the change in the internal energy, then is 3 halves n tilde R dt, no matter what. Because 3 halves nRT is the energy, the internal energy. And so therefore, there's no T right here. It's just 3 halves nR. 3 halves nRT is the internal energy, right? U is 3 halves n tilde RT, period. That's the internal energy for an ideal gas. So du, as long as n tilde is not changing, du is going to be 3 halves n R dt, no matter what, for these calculations. As long as n tilde is not changing. And again, if it changes, there's ionization. That will cause you to have to put in extra energy in order to raise the temperature, because some of the energy goes into changing the ionization. But if that's not happening, if you're well away from an ionization zone, then that's U, whether it's a constant pressure, constant volume, whatever. Okay, so if we want then the specific heat at constant pressure, so the specific heat at constant pressure is going to be, again, that ratio, dq over dt at constant pressure. In other words, how much heat you put in divided by the temperature change at constant pressure, because we want Cp. And so this time it's going to be du dt at constant pressure plus pdv dt at constant pressure, because again, remember that dq is du plus pdv. And so dq over dt will be du over dt plus pdv over dt. And then we have to say whether we're doing it at constant volume or constant pressure. Here we're doing it at constant pressure. And again, remember, that's what the vertical line, the subscript means, is we're evaluating this at constant pressure. So what questions do you have at this point? Yes?
What's that statement, no matter what?
No matter what, if n tilde is constant. If you want, I can put a comma here.
Yes.
No matter what, if, no matter what, if n tilde is constant. Yes. It wants to be right there, of course. Yes. Because the internal energy is 3 halves n tilde RT. The expression for the internal energy. And so now, if n tilde is not constant, then we would have a 3 halves RT dn tilde term as well. If n tilde is staying constant, dn tilde would be 0, and we don't have that term. Wait for people to catch up. Done with that expression, we have to figure out, okay, well, what is dV dt at constant pressure? What's the rate of change of volume with respect to temperature if we're holding the pressure constant? And again, the idea would be with our piston-cylinder arrangement. There's our cylinder, there's our piston, and we could imagine, I mean, in general, you just have heat flowing in through the walls, but we often like to think of, ooh, flames, we've got flames on the bottom of this, putting heat into that trapped fluid. And if it's at constant pressure, there's this pressure outside same pressure inside. P in equals P out if we're doing this at constant pressure. And so the heat that we're putting in will go partly into raising the temperature and partly into causing the piston to move up in order to keep the pressure the same as the pressure outside. Because if the piston was locked into place, raising the temperature would also raise the pressure. But we're trying to do this at constant pressure, so we let the piston slide. It's able to slide upwards frictionlessly with the walls, against the walls. And so when we heat it at constant pressure, we're partly putting energy in to raise the temperature, partly it's going to do PV work, and that will keep the pressure constant as it expands. So we're, quote unquote, wasting some of the energy we're putting in. It's not all going into raising the temperature. So therefore, the specific heat at constant pressure has to be bigger than the specific heat at constant volume. So my next line here is, but since Pivnert, PV equals N tilde RT, oh my gosh, we're doing more the chemist version of the ideal gas law. But again, this is all per unit mass. This is the volume per unit mass, 1 over the density. This is the number of moles per unit mass. Everything is per unit mass here. PV is nRT, so Pivnert, except now it's Pivnert, right? Because it's on N tilde Pivnert. Pivnert says, at constant P and N tilde, we have P dV dt at constant pressure is equal to N tilde R. And if that's not obvious to you, if we took differentials of both sides of this expression, what would I get? What's the differential? In other words, we could say the little change in PV is equal to the little change in N tilde RT. What's the differential of PV? In general, what's the differential of PV? Product rule. If I take the differential of a product, what do I do? What do you do if you take the derivative of the product? What's the derivative of Fg with respect to x? What's ddx of Fg? We are, it is. But what I'm trying to do here is show why this is true when P is constant. In other words, here I'm saying at constant P and N tilde, we have the PdT at constant pressures, N tilde R. And over here, I'm going to say, I'm just saying, as an aside, if you will, let's write down generically what this is. And then say, okay, but then if the constant, if we have constant pressure, we'll say, well, dP is 0. Yes? Yeah, if we did it as a derivative with respect to temperature, I could do that. I'm just going to write it as a differential, so generically I can say then this is going to be PdV plus VdP, and yeah, I could make it dt if I wanted, right, is equal to, and then if I do this one, R is the gas constant, that can change. So this would be, we could do it like T dN tilde plus N tilde times R. RT dN tilde plus, what am I trying to say? N tilde R dt, if I just take kind of generic differentials of both sides. Constant P and N tilde says dP equals 0, dN tilde is equal to 0. So you get VdP, I'm sorry, PdV is equal to n tilde r dt, and so that lets us say that dV over dt, when we're holding the pressure constant, is equal to n tilde times r. So that's the long-winded way of saying that that's true. And generically, this is what you would have a question.
After equal to on the third line, what is it?
Third line,
That, yes, we just guess that.
right here, dP is equal to 0.
Okay, sorry.
Okay, right here, RT dn tilde plus n tilde r dt. So I'm just taking the differential of that quantity, right? And the differential of Fg, generically, is Fdg plus GdF. So I'm just doing that here. R is a constant I can factor out. So the differential of n tilde RT is R times dn tilde times T plus n tilde times dt. And that's what I've written. Okay? And then here, I just divide d by dt. P dV dt. P dV dt is n tilde r, is what I was trying to get here. I just divide through by dt to get P dV dt at constant pressure is n tilde r. Look like you're not buying what I'm selling.
So why is that partial?
So I'm being a little sloppy here. Here's my little d's, and I just kept them there. So if you like, they get promoted to partial derivatives because of that. Yes. Eraser. Eraser. Where's an eraser? I just noticed I don't have an eraser. Oh, I hope it's not like hanging out between the board and the base and the wall there. What the hell? All right. There's going to be hell to pay. I shall return after I get an eraser. This is Tuesday.
Is the E&M exam on Monday or Thursday?
Monday.
I was just asking. I think my psych exam and this exam are the same time, same day. I don't know how that's possible.
E&M is the 8th. I thought it was the 11th.
Yes. I thought it was.
E&M is Monday. E&M is
Yeah,
Monday.
In the middle period, we need to talk about the final, because I put something on the syllabus that's wrong, because I misread the final exam schedule. I put it for Tuesday, Thursday, 2:10 to 4 classes. This is a Monday, Wednesday, 2:10 to 4 class, which isn't an official time slot. So we'll talk in the middle.
So what
So
day?
that's why.
We'll figure it out. We're going to figure it out.
It can't be Thursday.
Okay, I don't want it to be Thursday either. Yeah. I don't want it to be. I forget how much. We'll get to it, We're learning right now.
Yes.
We'll get to it, trust me. Okay, so we already know that this is still going to be 3/2 n tilde r. It's going to be the same thing as CV because this derivative is always 3/2 n r because du is always 3/2 n tilde r dt here. So as long as n tilde is constant again, this is going to be equal already to CV, which is equal to 3/2 n tilde r. So what we learned, and you may have seen this before, is that CP is CV plus n tilde r. And the assumption here is it's an ideal gas and constant n tilde. No change in the ionization. And again, it makes sense that CP is larger than CV because when you do it at constant, when you heat the gas at constant pressure, not all the heat inflow goes into changing the temperature. Some of it goes into the expansion of the gas that allows it to keep the pressure constant with the outside. But as it's expanding, it's doing work on the surroundings. So some of the heat that you're putting in is going into doing work on the surroundings in order to keep the pressure constant as opposed to raising the temperature. So you need extra heat in order to raise the temperature at constant pressure compared to constant volume. What questions do you have? Have y'all seen this before? Yes, no? Do you know? Maybe? Now you've seen it. You've definitely seen it now. Glorious! Glorious!
We've never seen any of the tilde in this aspect of the ratios.
Yeah, okay. Well, this is just because I'm doing it per unit mass. And because with the tilde we can say right?
Otherwise, we're
Yeah, there you go. That's right, yes. Yes. It's the knights who say yeep this time. Thank you. Okay. All right. Okay. Let everybody catch up here. Is everybody caught up? All right. So, for an adiabatic process, because remember, right, this is a pretty long derivation. You got to check in. Wait a minute. What are we doing? We're finding the adiabatic temperature gradient. The temperature gradient where a bubble rises and no heat flows into or out of it. So for an adiabatic process, the kind we're interested in right now, we're assuming our bubble rises fast enough, there's no time for heat to flow in or out of it. For an adiabatic process, dq is equal to 0. That's the statement of adiabaticity, if you will, that there's no heat flow in or out. dq is equal to 0. So that says that du, which generically is dq minus pdv, in this case is just minus pdv. du is minus pdv. But as before, from our beloved ideal gas law, we have that PdV plus VdP is N tilde R dt for the ideal gas law with constant, I'm going to keep adding that, with constant, PdV plus VdP, VdV is n tilde RDT. Right, that's what we wrote before over there, when dn tilde is equal to 0. Right? So now we're going to get what we call the adiabatic gas law out of this. It will be important to remember, it's not a separate gas law from the ideal gas law. It is the ideal gas law for the case of an adiabatic process where there's no heat flow in or out of the gas as it changes its conditions. Wait for everyone to catch up here. Are you caught up? Can I keep going? All right, so I feel we have to be extra like this week because everybody's been like. So, okay, here we go. All right, so using dt equals du over the specific heat at constant volume, because we said that Cv is du dt no matter what, if n tilde is constant, equals, okay, but now it's adiabatics, right? So here I'm right under this to emphasize. This is what happens when we're in an adiabatic situation here. This becomes minus PdV over Cv. Minus PdV over Cv, because we're adiabatic, ain't no dq in this case. We have, let's come back over here while you're catching up, and I am creating blackboard carnage. PdV plus VdV is equal to minus n tilde r over Cv PdV, because I have n tilde r dt, but dt is minus PdV over Cv, so I'm just plugging that in to the right-hand side of the nRdt over there on the PdV plus VdP line. Are you okay with that? Two, 4, 6, 8. Let's factor some stuff. That was a terrible call. All right. So this says that P times 1 plus n tilde r over Cv dV. So I'm putting all the dV terms on one side. And I'll move the dP term to the other, equals minus V dP. So just move the VdP to the other side. Took this over here, took this term over here. Just switch sides on those two terms. Oh, but look what we do then. So let's put over a common denominator here. This says that Cv plus n tilde r over Cv. So that's just putting what's inside the parentheses over a common denominator. And then I'm going to divide through by V, dV over V. And I'm going to divide through by P equals minus dP over P. got something like trying to log itself here, right? Ah. So, what's that? What's that? It's the other one, right? So this is the CV. What's the other one? CP. This is CP. CP, right? So we got CP over CV. Why, if only there was a name for that. What do we call CP over CV? It's relatively easy to think of. What was it? The other one. Yes, we called it the other one. So we say the other one. No, my hint is it's relatively easy to remember what we called it. Why, it's not a symbol from relativity, but gamma was what we called it. We called it, right? Gamma we defined to be CP over CV. So let's use that. So now we say, aha, gamma times dV over V is equal to minus dP over P. Aside, just mentioning in connection with this, for a monatomic ideal gas, gamma is 3/2 n tilde r plus n tilde r over 3/2 n tilde r equals 5/3. That'll be something to keep in mind. For an ideal gas, the monatomic ideal gas, we run into those not infrequently in astrophysics. Gamma, that ratio of specific heats, will be 5/3 because this is 3/2 plus 1 is 5/2 nr, so it would be 5/2 over 3/2, which is 5/3. Later, when we do white dwarfs and good stuff like that, we will find that for a relativistic gas, gamma is 4/3 instead of 5/3, and that will have significant import. But for a non-relativistic monatomic ideal gas, gamma is 5/3. 2, 4, 6, 8. This time we'll rhyme and integrate. Wow, it sure is going to be great. I hope my little things like that you do not hate.
There's too much on our plate.
Wow, okay. All right. And when that happens, it might more than you sate. To sate is to fully satisfy.
Okay.
S-A-T-E, right? So one can be satiated. Okay, so, ha, I came up with another one. How do you rate? Yes. Be late. Wow, of puns now, or of rhymes now, there is such a spate.
Right.
Yes.
If only I knew the meaning of C date.
Yes. Not in this class, you don't. That's right. Not in this or any date. Wow. All right then. So, okay. Integrate! Integrate. So, the integral of dV over V is natural log V. So we'll have gamma natural log V on the left side. On the right side, we'll have minus natural log P. And then we'll have to throw in an integration constant because I'm doing this as an indefinite integral. So A equals constant of integrity. A is our constant of integration here. So, now what are we going to do? 2, 4, 6, 8, before we did then integrate 2, 4, again, 2, what was it? I don't know. 2, 4, 6, 8. Now it's time to, who wants natural logarithms? How can you get rid of those? 2, 4, 6, 8. Now we exponentiate, right? Exponentiate. Exponentiate. So this says that v to the, well, this was supposed to be very explicit, e to the gamma natural log v is equal to e to the a times e to the minus log p, right? Because e to the a plus b quantity is e to the a times e to the b. So I've used that on the right-hand side. And over here, I can use the fact that e to the ab is the same thing as e to the a to the b, right? And over here, I use the fact that e to the a plus b is e to the a, e to the b. So those are the things I'm using here in going to my next step. So here, I can say that this is going to be e to the log v, over here, e to the natural logarithm of v to the power of gamma is a way to write e to the gamma log v. Make that clearly a gamma. What's e to the natural log of v? V. So this side is v to the power of gamma. And what's e to the minus log p? 1 over p. So on the other side, we have e to the a over p. V to the gamma is e to the a over p. Or in other words, p v to the gamma is equal to k, where k is a constant. In other words, we're just renaming our constant k. K is e to the a. So a is some constant. It's a constant of integration. So p v to the gamma is equal to k. K being some constant. This gets a box and an angelic choir that sings, it's the adiabatic gas law. Something like that. The choir needs to practice. Anyway. The adiabatic gas law. This is the adiabatic gas law. And I'll write it out explicitly to be sure you put this in, right? Note, this is not a new gas law separate from the ideal gas law. The adiabatic gas law is the ideal gas law for adiabatic processes. It's a special case of the ideal gas law. i.e., and I'll throw this in, we're not going to use this per se, for processes at constant entropy. Because remember we said that even if you're not super familiar with the concept of how this entropy stuff works, I didn't believe it until I took StatMech. I mean, I believed it. I knew people used it, but I'm like, what is that weird stuff? And then I took StatMech and I'm like, entropy! I know what it is now! That was one of those, sometimes you're like, you've been confused about something, you finally understand, like, wow! And that was one of those for me when I took StatMech. I'm like, I believe in entropy now! That was great. That was actually a very happy day. I still remember it, So if the entropy is constant, PV to the gamma is equal to some constant, and in fact, K depends on the entropy. The constant actually depends on the value of the entropy of the gas, really the entropy of the unit mass here, per unit mass here. And notice, another way to think of this is that if our bubble is rising, and its initial pressure and volume are P1 and V1, its final pressure and volume, P2 and V2, will be related to P1 and V1 like P1 V1 to the gamma is P2 V2 to the gamma because they're both equal to this same constant. So what the adiabatic gas law tells us is if I know the change in volume, I can calculate the change in pressure and vice versa. They're directly related to one another. The pressure and the volume of a parcel of a gas that is rising adiabatically, or in general, is adiabatic, no heat flow in or out, are related to one another by that relationship. What questions do you have? I'll take that as a statement. Yes. I won't make you repeat it for the camera. Okay. Basically, from her face, I can see that Catherine was thinking, could this possibly be any cooler or more interesting? And the answer is, it would be hard. It would be hard. Yes. Okay. So, since V is 1 over rho, and again, it's not generally true that V is 1 over rho, but if we're talking about the volume per unit mass, that's the reciprocal of the density, because the density is the mass per unit volume. So in our everything is per unit mass universe here, V is 1 over rho. Since V is 1 over rho, we can also write that P rho to the minus gamma is equal to some constant. Right? Because V to the gamma is 1 over rho to the gamma is rho to the minus gamma. So P rho to the minus gamma is constant. Or in other words, another way to write the adiabatic gas law is P is equal to K rho to the gamma. So the pressure and the density are directly related to one another in a gas that is undergoing an adiabatic process. Two, 4, 6, 8. Time to take logarithms. Another demo. Yeah, 2 more. 2, 4, 6, 8. Time to logarithmiate, which is now a word because it makes it a rhyme. Yes. 2, 4, 6, 8. Time to logarithmiate. All right. So let's logarithmiate here. Take logarithms of both sides. So plus taking logarithms. Logarithmification, something like that. Anyway, thus, the natural logarithm of P is equal to the natural logarithm of K plus gamma times the natural logarithm of the density. Right? Because the log of A to B is B log A. So the log of rho to the gamma is gamma log rho. So since we're talking about a bubble rising in a star. Let's differentiate with respect to R as our bubble rises. So, but first, note that if I take, then, better go over here because it's getting lower on the board and I'm trying to write scripty natural logarithms and that's going to turn into a disaster. So, wow, that was, okay, you don't want to be with me, huh? All right, fine. All right. Just came right out, okay. Okay, so, if I look at d log p dr, well, that's equal to d log p dp dp dr by the famous, from calculus, by the famous chain rule, right? By the chain rule, d log p dr is d log p dp dp dr. What's d log p dp? What's the derivative of log p with respect to p? Yes? Yeah, so I'm saying I'm rewriting d log p dr as d log p dp dp dr by the chain rule, right? Because, you know, good bad algebra, but good calculus, as my very first calc professor liked to say. I can cancel the dp's. Bad algebra, but good calculus. Really, it comes from taking a limit, blah, 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 and that's why it gets to work. What's the derivative of the natural logarithm of p with respect to p? I've forgotten that very fundamental factor. Yeah, 1 over p, 1 over p, right? The natural logarithm is a function whose derivative is 1 over the variable, right? So this is 1 over p dp dr. d log p dr is 1 over p dp dr. And so we'll use that, because then it's also going to be true that d log rho dr is 1 over rho dr. But first note that, and also then naturally by the same logic, d log rho dr is going to be 1 over rho d rho dr. So our derivative of both sides with respect to r says 1 over p dp dr for our bubble. So it's rising, its pressure is changing, and dp dr is the rate of change of pressure with respect to r as the bubble rises. 1 over p dp dr is equal to, what's the derivative of k? 0, because it's a constant, right? Is equal to gamma times 1 over rho d rho dr is the derivative of that expression over there. And thus, and I could have gotten this also from the original expression, and thus, but I wanted you to remember how log derivatives work. So, and thus, dp dr is equal to gamma times p over rho times d rho dr. And I promise this is heading somewhere, right? Because it's like, I was saying, you know, it's like, wow, this is like, you know, the adiabatic temperature gradient. And the subtitle was Moby Dick, because it takes a while to get here. Oh, but it's going to be so worth it. At least I think so. And I know Kathleen will think so. If I could just capture that, I'll come to late on use.
I'm so excited.
I can see it. I can see it. I can even feel it. That's right. Yes. Mind control works. He said, hoping it's true. Okay. Yes.
Can I get a quick confirmation?
Yes.
That it's 1 over P dPdr equals gamma 1 over rho d rho dr.
Correct. That's right. Correct. Yes. 1 over P dPdr is gamma times 1 over rho d rho dr.
Musically.
It is. That's right. Yes. Uh-huh. Yep. Right? The ideal gas law. Because remember, the ideal gas law still holds. The adiabatic gas law is not an independent gas law. It's the special case of the ideal gas law. Right? The ideal gas law as P, the ideal gas law, not as it is, P equals rho KT over mu times MH, the mass of hydrogen, as, I'm going to take logs again. And again, I said before, we could have gotten that relation directly from P equals K rho to the gamma, but it's actually easier to take the logs first. It's actually easy. Try it yourself and you'll see it's actually a bit easier to take the logarithms first and then use the chain rule thingy over there. So write it as log P is equal to log rho plus log T plus log of everything else plus log of K over mu MH, right? Because the logarithm of a product is the sum of the logarithms. So write it out as the sum of those three logarithms. Okay, so here's where we are right now. Here's where we're headed. We're almost there. We are so almost there. I can feel the tension building. Oh, we're going to have to take a break for, not yet, not yet. Still got a couple, but we'll have to take a break. Or we'll be like, oh, I can't stand it. But anyway, okay, so if mu is equal to constant, right? Mu is a constant. No change in the ionization, remember, because that's the mean molecular weight. Ionizing puts in more particles, lowers the mean molecular weight, so no change in ionization. So our bubble here is not close to an ionization zone. No change in ionization. Mu is constant, no change in ionization. We have, well, let's do those derivatives again. So we can say that 1 over P dPdr is equal to 1 over rho d rho dr plus 1 over T dt dr. Plus nothing, because K and U and MH are all constants. So dPdr is equal to P over rho d rho dr plus P over T dt dr, so I just multiply through by P, next half period for the rest of our story. Oh, we're almost there. Cliffhanger, that's right, cliffhanger. Yes. I'm tired. Tune in next semester for the. No. Like, oh, wow, this stuff sucks. Oh, but it's opposite day. Hooray! yeah, right. Exactly. Yeah. Oh, that's going to get really confusing quickly. Okay.
You start doing all the math wrong.
Yeah, that's right, that's right. Wow, that would surely have changed, wouldn't it? So, okay. Look at this one right here. Look at this one right here. The P over rho dr, why this is equal to 1 over gamma times dp dr from that earlier equation we had, right? From there, right? Because if I take 1 over gamma times dp dr, I get p over rho dr. So I can replace that first term on the left with 1 over gamma dp dr. So, dt dr for an adiabatic process solved after plugging that in here, right? So this is the 1 over gamma dp dr. So now solve for dt dr, and we get that it's equal to 1 minus 1 over gamma times t over b dp dr. Right? In other words, I just multiply through by t over p and pull this 1 over gamma dp dr term over to the other side after I multiply through by t over p, so it turns into t over something. Is that right? T over, yeah, it's supposed to be t over p dp dr. Yeah. Yeah, because the p's cancel. Wait, nope. Okay, now I'm confusing myself. Is that right? It's opposite day. That's right, that's right. Okay, just to be sure, I'm just going to put it all out here because I just jumped in my notes, because it's just obvious what's to do. So this would become t over p dp dr is equal to t over p times p over rho d rho dr plus, but that's the thing. This became 1 over gamma dp dr. That was what was still going on. That was 1 over gamma dp dr, which is why then it just turns into that. Equals t over p times 1 over gamma dp dr plus dt dr. And now I solve for dt dr. Just throw that other term over there, and it becomes what I am happily claiming here. Yes?
I'm just trying to see what goes right.
Yeah. So do you buy this? I just made the substitution that this term is 1 over gamma dp dr. Then I multiplied through by t over p, so I get t over p dp dr plus t over p 1 over gamma dp dr, because I'm multiplying everything through by t over p 1 over gamma dp dr, and when I multiply by t over p, this just becomes dt dr. So now, all right, to get really explicit here, T over P times dPdr, right? Minus T over P 1 over gamma dPdr equals dTdr. And then just factor. Right? In other words, factor out, this is T over P dPdr times 1 minus 1 over gamma. I'm just factoring this term to get the right-hand side of the other one. With my very neat handwriting. That's all. Is everybody happy? Oh, because it's opposite day. Yes. There we go. Is everybody sad?
Of course.
Wait. Wait. Oh, never mind. I don't know. Yeah. Okay. So. Oh, I'm so confused. It's back to not being opposite day anymore because I can't handle it. My brain is too fried. Okay. Woo! All right. And since it's not opposite day, that's a genuine woo! Okay. So now. But since P is equal to rho KT over mu MH, because it's still the ideal gas law holds here, that didn't stop. We have that T over P is equal to mu MH over rho K. And, so this bubble's rising, but it's in a star, so we've got our hydrostatic equilibrium equation for the surrounding gas, right? And from the equation of hydrostatic equilibrium, so now this is something that, because it's a star, which seems appropriate in an astrophysics class. dPdr is equal to, why, you all remember, right? dPdr is equal to, what is it? What's dPdr according to hydrostatic equilibrium? Everybody all at once? So this says pressure force per unit volume is the gravitational force per unit volume, which will be the mass per unit volume times the local gravitational acceleration. Right? Right. And meanwhile, the local gravitational acceleration, why, from Gauss's law, which applies just as surely to gravity as to E&M, because they both are inverse square laws. From Gauss's law, if m sub r is your radius, only the mass interior to your radius contributes a net gravitational force on you, just like in a ball of charge. Spherically symmetric, only the charge interior to your radius contributes an electrical force on you. Y'all know that, right? It's been, right? Yes? Yes? So, if I had a little cute little test mass, a little m right there, what would be the gravitational force on it due to that mass interior to its radius? What does Newton's law of gravity say? It says it would be, yeah, G m sub r, right? Mass interior radius r, over, like that's at radius r right there, over r squared over r squared And so if that would be the gravitational force on our cute little mass, what would its acceleration be? Whoops. That's why everybody was looking at me funny. Yes, there we go. I just forgot the rest of the M. Okay, so what's the local gravitational acceleration? And we'll put, yeah, okay. What's the local gravitational acceleration? Yeah, the force over the mass, right? So really I should say the gravitational force is minus because it's in the negative R direction, right? I mean, the opposite direction of the increasing R. So G is, divided through by our little test mass, it's equal to minus G M sub R over R squared. So dPdR is minus rho G M sub R over R squared. Golly, look what I just did, because I've already guaranteed you, you're going to have a question on the final where you're going to derive this from scratch, and you're going to say, well, you know, I know that from Gauss's law, because it applies just as well for gravity as for E and M classically, that the gravitational acceleration will, of course, be Gm sub R over R squared, and so then there's going to have to be a minus rho Gm sub R over R squared if I want the force per unit mass due to gravity. So we get to put that in for dPdR. Oh, look, there's dPdR right there, right? There's dPdR. So here it is. Here it is. We are right here. We're trying to get right here. Here it is. Here it is. dTdR adiabatic. In other words, before we had dTdR radiative, if radiation is carrying the heat flow, dTdR adiabatic, if it's convection for a rising bubble, but then we said, oh, but if there's convection, the actual temperature gradient is very close, it turns out, to the adiabatic gradient, and we're finding the adiabatic gradient here. dTdR adiabatic is equal to minus 1 over gamma times mu mh over k times g m sub r over r squared. This gets a box. This is where this journey has been headed. This is equation for B to complement equation for A, which was the other version of the temperature gradient, right? So in other words, on some level, we're saying dTdR is equal to equation for A versus equation for B, depending on whether it's radiative transport or convective transport. In the lovely homework that you're joyfully doing or will soon joyfully do, you get to make an if statement in your Excel sheet which says, do this equation if it's radiative, and use this equation for dTdR if it is convective. And we're about to get the condition for when the transport is convective in terms of gamma. So, what questions do you have? So again, what this has all been about is a rising bubble. We're finding the rate at which its temperature changes with height. dTdR is the rate at which our bubble's temperature changes with height as it rises and does work against its surroundings, causing it to cool off. And remember, let's see, do you remember? It'll keep on rising if its temperature compares how to the temperature of the surrounding gas. Does it need to stay hotter than the surrounding gas or cooler than the surrounding gas to keep on rising? It has to stay hotter because its pressure compared to that of the surrounding gas, is it greater than, less than, or equal to the pressure of the surrounding gas? Was that great?
Less than hotter.
If the bubble's pressure was greater than the surrounding gas, what would it do?
Expand.
Very quickly it would expand. If it was less than the pressure of the surrounding gas, what would it do? But it's gently rising. I'm gently rising. So the pressure compares how to the surrounding gas? It stays equal to it. It stays equal to the pressure of the surrounding gas. Its pressure is the same. So from the ideal gas law, its density times its temperature is the same because P is rho kT over mu mh. K and mu mh are constants. So if they're not changing ionization, we're not changing ionization, mu stays constant. So if the pressure is the same inside and outside, density times temperature is the same inside and outside. So if it's going to stay buoyant, its density has to compare how to the density of the surroundings. Does it need to be denser or less dense than the surroundings to want to keep on floating upwards? Yeah, it's got to be less dense, right? It's less dense things that are buoyant, that want to rise. So our bubble's density has to be less than its surroundings, but density times temperature is the same as the surroundings. So if the density is less than the surroundings, what must be true about its temperature compared to the surroundings? The temperature has to be higher. If rho T is the same and rho is lower, T's got to be higher inside the bubble for it to be buoyant. And it won't be buoyant if it went the other way. If it's cooler than its surroundings, it will also be denser than its surroundings, and it won't want to keep rising. But the condition for convection is it does want to keep rising. That's what our whole, taking the long view here, right? Our whole thing here has been about find the conditions under which the bubble's going to keep rising. Well, that means it's got to be buoyant. Well, that means its density's got to be less than the surroundings, but its pressure is the same. So rho T is the same. So if rho is less, T is more. That's everything in a nutshell, along with math. There's the adiabatic temperature gradient. But now, does it keep rising? It says, okay, it's going to have its temperature changing. We want it to stay hotter. This is like a review. We want it to stay hotter than its surroundings. Let's see. As it's rising, is its temperature increasing or decreasing? As it's rising, it's expanding. It's doing PV work on its surroundings at the expense of its internal energy. No heat is flowing in or out of our bubble, so its internal energy changes only due to that PV work. It's expanding against surroundings. So is its internal energy increasing or decreasing as it does work on its surroundings, expanding against them? Decreasing. If you do work on something, I mean, you're burning fuel, right? But if our bubble doesn't have a fuel source on it, is doing work on its surroundings, that's at the expense of its internal energy. It's using up internal energy to do that work. But the internal energy depends only on the temperature. If n tilde is constant, the internal energy per unit mass is 3/2 n tilde RT. So if its internal energy is decreasing, what is happening to its temperature? As the bubble rises, its internal energy is decreasing because it's spending some of it to do work on its surroundings as it expands. And so its temperature must decrease. It's cooling down as it rises. What about the surrounding fluid? That's not necessarily rising or falling, but the surrounding fluid, we know if it was just stably stratified, how does temperature depend on height in the star's atmosphere? Does it increase as you go higher up? Does it decrease as you go higher up? It decreases. So the surroundings are getting cooler, The bubble is getting cooler, but we want the bubble to stay hotter than its surroundings. So the bubble has to cool less than its surroundings did. It's cooling down, the surroundings are also getting cooler. They're not cooling down, it's just moving into areas where it is cooler already. So the bubble has to find that its temperature is not decreasing as fast as the temperature of its surroundings in order to stay buoyant, because then it'll stay warmer than its surroundings. Well, the rate at which its temperature is changing is this. That's its rate of change of temperature with respect to distance as it's rising. And so this goes back to what we said a while ago, that the condition for convection is that in magnitude, use absolute values so we don't have to be like, oh God, negative numbers, when they get smaller, they become more negative, oh my God. So make it just absolute values here. The magnitude of the rate at which the bubble's temperature is decreasing, the adiabatic temperature gradient, should be smaller than the surrounding temperature gradient so that it's not cooling down as fast as the surroundings are. And then we said, okay, so if we want to figure out if convection is going to take place, one approach would be assume it's not. Assume that radiation is transporting the energy and calculate equation 4a. What would be the temperature gradient from equation 4a? And then calculate equation 4b. What would be the adiabatic temperature gradient? And make the comparison. Make the comparison. And if the adiabatic temperature gradient is smaller than the radiative temperature gradient, then the bubble will stay warmer than its surroundings and it'll be wanting to rise, and that'll favor convection to set in, and vice versa. Good thing this is being recorded so that you can watch it later, right? Because I've said a lot here, but that was the summary of everything we've said, of what the conditions are for convection. Holds in Earth's atmosphere too. We are in the troposphere. We live in the troposphere where you can have convection in the atmosphere. The temperature of our atmosphere where we are, near the surface, decreases with increasing height. You know, if you go on a mountain, it's cold up there, right? So temperature decreases with height. So it could be that a rising bubble of air, that its temperature decreases slower than that of the surrounding air, and then you'll have convection. And so that's why you have convection in the troposphere. If it's especially vigorous, why those bubbles could rise and water vapor in them, and as they cool, could condense into clouds and make thunder boomers and all that kind of good stuff. Why, when you're flying your airplane and you drop into the troposphere, you can get this, ladies and gentlemen and everybody, please fasten your seatbelts and all that kind of good stuff, right? Okay. But planes like to fly into the stratosphere. In the stratosphere, there's ozone, O3, that can absorb ultraviolet light from the sun. And because there's more ultraviolet light getting absorbed higher up, because there's more ultraviolet light hitting the upper atmosphere than the lower atmosphere, because some of it's getting absorbed, in the stratosphere there is a temperature inversion. Temperature increases with altitude instead of decreasing with altitude, making it impossible for a bubble to be buoyant as it rises, because its temperature is cooling, the surroundings are getting hotter. It's impossible for it to stay hotter than the surroundings when it's cooling down and the surroundings are getting hotter. So the stratosphere is called the stratosphere because it is stratified. It doesn't have convection in it. So you fly your plane in the stratosphere because, first of all, the air pressure is lower there. There's less air drag. Second of all, it's a smoother ride because you're in a region where you're not going to see convection. Unless there's vigorous convection in the troposphere below, and then bubbles just from their inertia, from their momentum, can come up into the stratosphere. They can overshoot the boundary and buffet your airplane, and when they sink on the way back down, buffet your airplane. So that's why you can hit turbulence, quote unquote, even when you're flying in the stratosphere. You're hitting overshooting convection from the troposphere. happens. So, Dr. Cheese would like this because I'm talking about flight, right? So, right? So, it's just astrophysics where we talk about all this stuff. Happens in Earth all the time. Okay, I feel like there's something else I was going to mention here because I like these connections. I might have mentioned before that cumulus clouds, right, the mashed potato clouds, right, or the cotton ball clouds, right? I see a puppy, really, I see Satan, you know, those kind of clouds, right? Those are convective, right? So in other words, air is rising, and as it expands and cools, water vapor can condense into droplets. Gets high enough, they can freeze into little ice particles. Why do cumulus clouds look like puffy cotton balls and all that sort of thing? Because they are showing you the turbulent convective air. The droplets are forming in turbulent convective air, and so that's what gives them their characteristic appearance like that. If you've never done it before, when you see clouds, when you see a lot of cumulus clouds and the weather's getting cloudy and stuff like that, stare at one for a while, because you can literally see them growing. You can literally see them getting bigger, condensation happening. It's really cool. And then you can say, oh yeah, back in astrophysics we talked about that. Why, this is so cool. And it's cool because it's cooling off and it's condensing and all that. It's cool in every possible way. Wow, you know, yep. Right. So, good stuff, I do have to say. Oh yeah, one more thing. That's the other thing I was going to say. So, if a temperature inversion forms over a city, it gets really polluted. And LA is prone to this. If you get a temperature inversion, where temperature rises with altitude, you don't get convection, which means all the pollution is trapped near the ground. Because convection can carry it up and away to high altitudes and they can get caught and blow away. If you get a temperature inversion over a city, they'll just say, oh, there's an inversion today. It means there's a temperature inversion. It suppresses convection and it traps air pollution near the ground and gives you a bad AQI day, essentially. And that can happen in other places too, but LA is particularly prone to that sort of thing. Okay, fun stuff! Yeah, fun stuff. Exactly. Yes. Okay. Yes.
Is that like the mean we talk about?
Yeah. Well, no, another thing. No, a heat dome. I think that's just it's a lot higher, per se. Right. In other words, you have a. If the air quality is bad in your heat dome, then there's an inversion to go along with it. But I think the dome itself isn't necessarily coming along with that. Although, I could be wrong. That would be worth checking into. But yeah. So, yep. And certainly, I always love it when you see like a giant H going overhead, like the high pressure system. Right? You see it on the map, and so every once in a while you go outside, oh my God, it's over me. This giant H is going over that, all that. The air is higher pressure there, and the atmosphere is a little thicker there. It's a little taller there. It's a little less tall over lows, and those go around and have lots of fun. In a low pressure system, the pressure is going to be increasing as you move further away from it, because it's a low pressure system, and a high pressure system other way around. So low pressure systems are the ones that tend to be distinctively cyclonic, have rotation around them. Highs do too, but low pressure systems have more vigorous rotation and can be hurricanes and stuff like that, because if you've got air moving around in a circle, what's the net force on a parcel of air that's moving around in a circle? Is it inwards or outwards? Inwards, because it's got a centripetal acceleration. If you have a low pressure system, the pressure is increasing the further away from the center. So you have a parcel of air. If I'm if I'm the low, here's this parcel of air that wants to rotate around me. If the pressure is higher on the outside of the parcel than it is on the inside of the parcel, the net pressure force is inwards and can provide the centripetal force to maintain that uniform circular motion. And so a low pressure is well set up to maintain circulating air around it, which circulates because of the Coriolis force, because of the fact that Earth is rotating. If you have a high pressure system, that ain't working so well, because with a high pressure system, the pressure gradient is putting a force that's outwards on the parcel instead of inwards on the parcel, which is why hurricanes are low pressure systems, not high pressure systems. A high pressure system can't make a hurricane because it can't produce sustained strong rotation like that. But a low pressure system can. Wow, fluid dynamics, astrophysics, hurricanes, ooh, ah, it's great. It's fantastic. Okay. But let's get back to some astrophysics fun here. So we're going to get now a nice expression for when convection will occur, and that's what you'll see in the spreadsheet, basically. There will be a column that lists values of d log p, d log t, and based on that, it tells you whether there's convection or radiative transport. So, since in a star, dt dr is less than 0, it's getting cooler as you go higher up as the radius from the center increases. The absolute value of the temperature gradient adiabatic being, what's that subscript say? Actual, ACT, actual, being greater than, so the outside gradient being steeper than the inside of the bubble gradient, dt dr adiabatic becomes, take away the absolute value sign because we want to confuse ourselves, dt dr actual is less than dt dr adiabatic when you take away the absolute value sign. That always works that way, right? In other words, if you have negative quantities, when you take away the absolute value sign, it's going to change the direction of inequality. So, for example, the absolute value of -3 compared to the absolute value of -2. Which way should I put the inequality here? Yeah, the absolute value of -3 is greater than the absolute value of -2. Take away the absolute value signs, I'm comparing two negative quantities. The adiabatic gradient is negative, the actual rate is negative because the bubble's temperature is decreasing with height. The outside surroundings decreasing with height, their temperature. If I take away the absolute value sign, now which way do I put the inequality sign? This way, right? -2 is greater than -3, right? Because bigger negative numbers are smaller, so to speak, right? So if I take, these quantities are both negative, so when I take away the absolute value sign, the inequality switches directions. And so the condition for convection is that dt dr, I'll move over here because it gets so hard for me to write them down. Okay, gotta get some more chalk here. Or fully use the chalk I have. Becomes dt dr actual is less than, the adiabatic gradient was 1 over 1 minus gamma t over p dr which then we decorated up with the ideal gas law, but it goes back to it was the adiabatic gradient, a couple lines up was that the adiabatic gradient is 1 over 1 quantity 1 minus 1 over gamma T over P to PDR, what I just wrote there, that is the adiabatic temperature gradient right there. So the actual temperature gradient needs to be smaller than the adiabatic gradient for convection. You mind what I'm saying? Does that make sense? That was higher up. Right? That was right there. That was right there. And then we did a few more lines with the ideal gas law and the equation of static equilibrium. We got the beautiful equation 4B, but a little higher up we got that equation that, okay. So, okay, let's have fun moving things around. So this is going to say that 1 over 1 minus gamma is greater than T over P dP dr dr dt. So, in other words, what I did here was, I'll just be explicit. So, what I'm going to do here is, so I'm going to say that, what am I doing here? Yeah, so I'm going to multiply through by the reciprocal of dt dr, which is dr dt. You get to do that. And so I'm going to divide by dt dr and divide by 1 over 1, divide by 1 minus 1 over gamma. So I've done that. And then the inequality switches signs again. Parentheses here. dt dr is less than 0. So when we divide both sides by dt dr, we must switch the inequality. We must reverse the inequality. Right? Inequalities are a little tricky to work with because you have to keep track of these things. If you multiply or divide by a negative quantity, you switch the inequality. Right? So for example, if I had minus 3 is less than minus 2, right? And then I divide by minus 2, or divide by minus 3, right? Then I would get 1 over here and 2/3 over here. What happened to the direction of the inequality? Divide by minus 3. What happened? Now which way does the inequality point? This way, right? So when you multiply or divide by a negative quantity, you flip the inequality. You have to keep those things in mind. They're a pain in the schnook to do. But here, I divided by the negative quantity, dt dr, which is dr dt. So I had to flip that sign right there. Okay? 2, 4, 6, 8. Let's multiply through by gamma. Or no, this is, okay. Nobody called me on that. Nobody called me on that. I'm so sad that I messed up. But also that nobody called me on it. Right, it's 1, I divided through by 1 over, divided through by 1 minus 1 over gamma. 2, 4, 6, 8, multiplied by gamma over gamma. Right? So this becomes gamma. This becomes, come on, Chalk, you can make this far, just a little more. Gamma over gamma minus 1, and just multiplied by gamma over gamma. Gamma over gamma minus 1 is greater than T over P, dP dr, dr dt. But in another fine example of bad algebra but good calculus, the dr's cancel. Put another way, dP dr dr dt is the chain rule that says, well, that's dP dt. Right? dP dt is dP dr dr dt. This right here, that's dP dt. Happy with that? That's dP dp dt. Chain rule says dp dr dr dt is dp dt. So we can say that our next step is that gamma over gamma minus 1 needs to be greater than t over p dp dt. Gamma over gamma minus 1 needs to be greater than t over p dp dt. But dp over p is the differential of the natural logarithm of p, is it not? Right? D log p is 1 over p dp. If you're taking a derivative with respect to x, d log p dx, like we were doing before, would be 1 over p dp dx. Okay, get rid of the dx part. dp over d log p is 1 over p dp. So dp over p is d log p. Are you buying what I'm selling? Is that making sense? Okay, buy the derivative of the logarithm. The differential of the logarithm is 1 over of p is 1 over p dp. And similarly, I get to say that dt over t, why that's going to be d log t. So in other words, t over p dp dt can be rewritten as the following, at first, seemingly confusing expression. So t over p dp dt, or you could rewrite that as d log p over d log t. So that first seems like a weird expression. The derivative of the logarithm of p with respect to the logarithm of t. And don't be scared by it because it's really just t over p dp dt, which does not look scary. D log t is t over p dp dt, but astronomers love to just say d log t instead. And so we'll do that. But it's just t over p dp dt. It's just another way to say t over p dp dt. If you made a table of logarithm of p values and another table of logarithm of t values and took little changes in log p and little changes in log t and took the limit as everything goes to 0, that would be d log p d log p d log t, and it would be the same thing as t over p dp dt. So d log p d log t needs to be less than gamma over gamma minus 1. Draw a box around it. Right? Because I'm just reversing the order. Flip them around. The inequality changes when you change the two sides, right? In other words, if x is greater than y, then y is less than x. So I'm just flipping them around. This is the condition for convection to occur. That's the condition under which convection will occur. But that, yes. D log p d log t is the condition under which convection will occur. When you're doing the homework, one of the columns that comes out of the StatStar static stellar evolution, not evolution, stellar model code that is this code that comes with the book. You can download it and play with yourself. It's why I made the models using StackStar. Well, you can download one that they already had, but it doesn't have enough sig figs. So I made one more, maybe not entirely sig figs, but in this case. Anyway, now let's look at a monatomic ideal gas. Anybody remember what was gamma for a monatomic ideal gas? Mine's back a few pages. It's 5/3. Monatomic ideal gas, gamma is 5/3. So that says gamma over gamma minus 1 is going to be 5/3 over 2/3, right? Because 5/3 minus 3/3 is 2/3 on the bottom there, equals 5/2, affectionately known as 2.5. And so when you're doing the homework, why, there's a column that lists values of d log p, d log t, and if that cell is more than 2.5, then you know that, so then if we put in what we've got there, then, so our condition is going to be d log p, d log t is less than 2.5. So in that table, you'll see, oh, there's d log p, d log t values, and if they're less than 2.5, why, then it's convection, and you use equation 4b to calculate dTdr. And if it's more than 2.5, it's radiative, and you use the other equation. So you will have equals if in Excel, value of the corresponding entry is less than 2.5, comma, and then the way if works is it's if some cell is less than some value, let's say. If that's true, you apply the first formula, and if it's false, you apply the second formula. So that's how you can do a single column of values where it's what you put in there depends on the values of cells in some other column. So you'll see it as you're doing that. So you'll use the if function in Excel to go to the, I know, I'm as happy as you. To go to the list of d log p, d log t values from the StackStar model, and that will tell you whether each cell, it should use the first formula put into the if statement or the second formula put in the if statement. And one formula is the convection formula, and the other is the radiative transport formula. Now you put in 4a and 4b into the two slots in the if statement. And strangely enough, we're done. That's it. Yeah, I know. Until next semester. Yeah, it's going to be great. We're going to build stellar models next semester. It's going to be awesome. Yes. I know. It's going to be great. It's going to be awesome. We're going to build stellar models. Then we're going to kill stars, turn them into white dwarfs, turn them into neutron stars, turn them into black holes. And then we're going to we're going to make a universe. It's going to be all kinds of stuff. It's going to be awesome. Yep. So we've built our toolkit. Right? I love this stuff, but it's kind of like, this is the blocks sliding down the planes that you need to know before you can do the other cool stuff. Background physics, there's a lot of it, which is cool on its own, but it gets even cooler stuff. Alright.